It's part 7, and it is the neural integration now of synaptic potentials. And so just on the previous page, from where we are at this moment, we were discussing the synapse. And we spoke briefly about the release of neurotransmitter. How did that happen? Is the action potential came down, calcium crossed over the membrane, and the presence of calcium stimulated the movement of these vesicles containing neurotransmitter to be released into the synapse. They streamed across the synapse and bound to chemically gated channels here. And you actually have options. We can have a chemically gated channel that allows sodium, or we can have a chemically gated channel that allows potassium to pass through. Okay, so in this case, we were more concerned about how this arrangement works, just the mechanics of the synapse itself. Okay, now I'm going to be more concerned with what the potential is. Okay, so in this case, I have actually opened a channel with sodium, then I'm going to get a little depolarization. If I open a channel with potassium specifically, I'm going to get, instead of a depolarization, I'm going to get a hyperpolarization. Okay, this is inhibition. So we have something here called an inhibitory postsynaptic potential, abbreviated IPSP. And then we get a excitatory postsynaptic potential, abbreviated EPSP. And let's be reminded here from this diagram, what is resting potential? Resting potential is where we've pumped the sodium out and the potassium in, and these channels are essentially closed. And so sodium remains outside. Potassium channel is leaky and allows a little bit of potassium to come through. And hence there's a fall of parity here. There's going to be a slightly positive charge on the outside and a slightly negative charge on the inside. Okay, and so let's think about if we selectively open a channel. I have maybe a neurotransmitter that when bound, it will bind here and will open the sodium channel, and in so doing, sodium passes through and we get depolarization. That's the definition of depolarization, is opening a sodium channel. Okay, because the positive moves toward the negative, and we're going to depolarize. We're going to reduce the voltage. Okay, over here, if I selectively open potassium, I'm letting more potassium come through, and I'm creating more positive charge. And so now the positive charge is going to increase. The negative charge will also concomitantly increase, and we'll have more voltage across here. We're going to have more than 70. Okay? That's the idea that we're dealing with here. Here we are at resting potential, which is a minus 70 millivolts, and we're minding our own business, except suddenly acetylcholine or some other neurotransmitter opens up a channel and sodium comes through a little bit. So our postsynaptic potential, our membrane and the far side of the synapse, is going to become, how shall I say, charged with EMF. And there's going to be a slight depolarization. Okay, we're going to call it an EPSP. And then, on the other hand, if acetylcholine were to open up a potassium channel, which it does do from time to time, the vagus does that in the heart. The heart is slowed down by the vagus when the vagus opens up a potassium channel. The heart wants to actually, of its own sort of construction, it would like to go about 110 beats per minute if you gave it its own sort of bridle, as it were, but instead the vagus is holding it back with a little bit of inhibition and slows it down to resting rate heart rate. Okay, so this is a inhibitory postsynaptic potential. Now they talk here about the integration of these things, and we come over here to take a look at what that could possibly mean. And the idea here is that in many cases, particularly in the central nervous system, a cell body has many connections to other cell bodies and other parts of the brain. Right, so you can remember all of the different types of flowers and all the different kinds of colors that you've ever seen. So there's many types of stimulation that can happen here. But here we're just going to take a look at a single synapse. Do you see that right there? And they've identified it as excitatory, which means it's going to open up a sodium channel. So here I have a little stimulus, not enough to reach threshold. I have another stimulus, again, not enough of its own volition to reach threshold. And then over here, I get two stimuli very close together, and they will sum in terms of the EMF produced on the postsynaptic membrane, and we're going to get over threshold. And now I have a depolarization, and the signal from the first neuron will travel to the second neuron, okay, which means that the action potential coming down here will release neurotransmitters in adequate amounts in order for there to be enough to create an action potential in this next membrane. Okay, so we have that kind of integration that can happen. These are both excitatory, the signals when they come close together this way. Now we're dealing with two completely different synapses, but they are both E1, E2, which means excitatory. They're both channels for sodium, and so that means that sodium is going to flow. If I stimulate them both at the same moment, they will sum together, and they will provide us with a greater than threshold stimulus, and we get our action potential here. Okay, now here, a little bit more complicated. We have an excitatory situation and we have an inhibitory situation. Here we get the inhibitory to function, and you'll notice that we get depolarization, or rather hyperpolarization, inhibition. So this is an IPSP. Then we're going to have a sum of excitatory and inhibitory taken together. What if we were to stimulate both at the same time? Well, they're trying to draw this here, the artist. I don't know if they've accomplished it or not, but we should get a flat line through here because they cancel each other out. Okay? So that's another kind of integration that happens. Okay, so, and then they do talk about over here, they give us some diagrams to describe what we've just been through. And here they do talk about presynaptic inhibition. Presynaptic inhibition is something that we covered just previously, and it has to do with the common use of opiates. And I gave you an example. We're about to, in our next section here, deal with neurotransmitters. Take a look at what that looks like. And so I want to come back here for just a moment and review something that I drew in here. Here is a neuron. In this case, the neuron is stimulated by opiates. Okay, morphine would be one such opiate. And of course, our own endorphins would be extremely strong in the situation if they bound here. Okay, and what's going on is that we get a signal down here, and the neurotransmitter of interest coming from here is going to be GABA. GABA is almost universally inhibitory, and it's going to be used to open potassium channels. And so as the signal is coming down, it's going to run into a hyperpolarization. And if there's enough opiate stimulus and thus enough GABA release, there's going to be enough inhibition that will actually prevent anything from happening it could just prevent a little bit from happening. Okay, so you can use moderate amounts, and that will reduce the outcome down here. Or you can use a lot, and it will reduce it quite a lot. Okay, so we just have to remember that GABA is our almost universal molecule of, how shall I say, calming things down or inhibiting various functions.